Hey guys, in this video I'm going to show you that in rotational motion, angular momentum is conserved and rotational energy is not. So this is very similar to the case that in collisions, energy is only conserved if the collision is completely elastic. Most collisions are inelastic. In this case, I'm going to have an inelastic collision with a rotating object. So I have this disc right here which is rotating. It's going to be rotating. It's a very, very heavy disc of a moment of inertia, which I know already. Actually, I used another video to find the moment of inertia of this disc because it was actually not easy. So if you want to check out that video, that's an application of conservation of energy. But for this purpose, I just want to have this disc moving, and then I want to drop this ring, which is also pretty heavy, on the disc, and I want to see if energy is conserved or if momentum is conserved.
So the theoretical part of this is going to be pretty simple. We have conservation of energy, and this is all kinetic energy because there's no potential going on here. This is very similar to the condition for elastic collisions. And we have conservation of momentum. In this case, this is angular momentum. So I'm going to rewrite those as initial and final. I've labeled this K-rot because it's all rotational kinetic energy, and this is the angular momentum. So now I'm just going to put in the definitions of those. So here we are going to know the moment of inertias. We are going to measure the angular speeds initially, and then we are going to solve these equations to find the final angular speed. So I'm going to solve for those guys in the next line. So I've labeled our two predictions as final speed energy conservation, final speed angular momentum conservation. And now I need to work out a little bit what these guys are, because the initial is going to be my big heavy disk. And this is the thing which I spent another video finding. You don't necessarily have to know where it comes from, but that's experimentally determined by me. The final moment of inertia is going to be the initial plus the effect of the ring, because now it's just a spinning disk with a ring on top of it. This is the mass and radius of a ring. It so happened that the mass of that ring is about half a kilo, 444 grams, with a radius of 8.95 centimeters. So if I calculate that out, I get around 0.032 kilogram meters squared. So it's an increase of not very much, 0.03, about 10% or so. So it's a significant increase and enough so that we should be able to determine which one of these two is actually correct.
All right, so to get the data for this experiment, I'm going to use some video tracking software. This is Video Physics on the iPad. So what's really cool about this, I'll just show you the video first. You can see me, and I'm going to drop this ring onto the disk, and then it's going to slow down. I'm going to be able to track that little red dot, get the position and velocity, and that's how we're going to get the data for this experiment. First thing we have to do to use this program is to set the scale. So those two dots here are telling the program that the disk is 25 centimeters across, which I've just measured, and I put the origin in the center. What's really nice is now I can just set this thing at a point, and I can tell the program to track that red dot. And so now I just click track, and the program should track that thing around automatically. And so when I drop it, it'll see it slowing down, and then we'll just get a bunch of data from this. So I'm just going to fast forward through this because the data taking takes a little bit of time. Okay, now we've got a bunch of dots which show the position of the red dot at different times. We can go over to the data. You can see we have a nice circle showing in the XY plane the position of the red dot. And most importantly, we have X and Y position. Here's the X position and velocity, and here's the Y position and velocity. And that's what we're going to need to measure the change in velocity, or the change in angular speed of the disk. Okay, so I've pulled up my data in Logger Pro. You can see the X and Y position and velocity plots over here. I've added a speed column. So because we want to know the angular speed of the disk, we need to know the speed of that point as it goes around. The speed is going to be the X component of the velocity squared plus the Y component of the velocity squared square rooted. That's, of course, speed, and that's here. So let's plot that thing, see what it looks like. So there's a fair amount of scatter, but I think it looks pretty good. We have a constant speed here before the disk gets hit with the ring. Then the interaction happens here, and then down here we have the ring and the disk moving together. Friction is acting on the system, so that's decreasing the speed over time. Cool, so I want to know the speed before the interaction. That's right here. That looks pretty constant to me, so I'm just going to take an average of that. That is just going to statistics. and the average there is 11.01. Oh, sorry, the mean is 11.42. Okay, and to get the velocity after the collision, what I'm going to do is I'm going to fit a line to this data, which I think looks good. So that's analyze linear fit, pull out a line. So the equation for our line is mt plus b. There's our slope, there's our b-intercept. And to get out the actual speed, I'm going to pick a time when I think the interaction happens, right about there. That looks like 3.9 seconds. So I'm going to say the interaction happens at 3.9 seconds. I'm going to plug that into the equation here, and that's the speed that I'm going to use. So now I can go back and take that data, I can go back to my whiteboard, and I can check to see if, based on our prediction for energy being conserved versus velocity versus momentum being conserved, does that speed correspond to one of those two possibilities?
Okay, so now I've done the experiment. What I got for the slope of that line afterwards was negative 0.1428, that right there. Here's the intercept. I also had the root mean squared error on that. My initial velocity before the collision was 11.42. My final velocity, I'm going to plug in a time of 3.9 seconds into the slope equation here. My answer is 10.13, and you can think of the root mean squared error as the error on this value. Of course, now I want to plug them in up here, so I need them instead to be velocities. I want them to be omegas. Remember, the size of the inner disk is 3.2 centimeters in radius, so I can just divide these guys by the radius to get the angular speed. There are the values right there. I've also included the error because we're going to want to use that when we say, okay, which one of these are more correct. We want to be able to have the error to tell us how right we are. So now I want to find the theoretical values from plugging in my values for I here and into here and here to get the theoretical values from energy conservation and from momentum conservation. We find that if energy is conserved, we expect the velocity to be 3.36943 radians per second, and if momentum is conserved, we expect 3.18124. So first, check that we think our accuracy is 0.07, so we should definitely be able to differentiate between these two. So that's 7, and the difference is 18 to 36, and so we should definitely be able to determine which one of these is more correct. And actually look at our answer, 3.166. It is very clearly closer to the conservation of momentum answer rather than the conservation of energy answer. We can also think about how many standard errors away would the energy answer have to be true. This is 1 sigma. We can start adding sigmas and see how many it takes to encompass 3.36. 1 sigma is 3.24, not big enough. 2 sigma is 3.31, still not big enough. 3 sigma is 3.39, so that is big enough. So that means that up to 2 standard deviations away, we still don't come across that value. So if you know anything about error analysis, what that means is that if we continued repeating this experiment and continued getting these values, 99.7% of those values would confirm angular momentum conservation rather than energy conservation. Of course, we can't ever be sure about these things because this is an experiment, but this value tells us that it's roughly, with a 99.7% certainty, we can say that momentum is the thing that is conserved, not energy, in rotational motion. Okay, great. So I hope this has convinced you that we cannot use energy conservation in rotational motion. We must use angular momentum conservation. I see this a lot on exams, and so I want to make that clear. It may be hard to sort of conceptualize and intuit why that's true, but at the very least we can do an experiment and we can see that in this case, angular momentum is the thing that's conserved and rotational energy is not conserved. Okay, great. Thank you for watching this video, and I will see you guys next class.